This section continues the last in our practice of the definite integral. These problems will be a little bit less straightforward in that you will have to use that substitution that we learned back with the indefinite integral. So we're going to again practice evaluating definite integrals, and then toward the end we're going to find out how to find the average value of a function. First of all, let's kind of compare some of the rules from the definite to the indefinite. Pretty much the same except for the limits. I want to really call your attention to these first two. Notice if the limits are the same, your area is going to be 0. If you think about if this is A and this is B and this is your function and you're trying to find the area, well, from A to B you would have an area. But if that area was just on A, you would have 0, and that's that case. Also, if you reverse the limits of integration, you would negate the area. We talked about last time how if the function falls underneath the graph, we would call the area above positive and the area below, that would be considered negative area. So if we reverse those limits of integration, it reverses the subtraction, you have an opposite sign. Now the other rules are pretty much the same. If you have a constant, you can pull it out in front. Addition and subtraction, you can break it apart, again keeping those same limits. And sometimes if you have some boundaries between A and B, and for some reason you'd want to split that up, where C is between A and B, you are allowed to do that. So let's just dive in and look at some of these problems. We're going to be asked to find the definite integral. Well, this looks pretty complicated, and as you recall, let's rewrite the square root as an exponent. And when you have that, you might want to use that u substitution. So we're going to let u equal to 5x squared plus 4. Then we're going to take the derivative, and don't forget the dx. Now this is where you kind of compare what you have and what you need. So let's come over here. I have x dx, which would be just this part. So I really need to kind of get rid of that 10. So I can do that as long as it's a constant. So 1/10 du equals x dx. So let's see if I can make that substitution. I'm not going to worry about the limits of integration. I realize there is a process that you can change those limits, but I'm going to choose not to do that right now. So let's see, I have this, so that's going to be u to the half power, x dx. What does that equal to? It's 1/10 du. I'm going to go ahead and integrate that. Let's see what we come up with. We keep the constant. We add 1 to the exponent, so that would be 3/2, and then we're going to divide by that exponent or multiply by the reciprocal. Now usually we would put plus c if that's an indefinite integral, but we're not done. Let's go back and figure out, well, let's go back and put in x, because these limits are in terms of x. So really what we have is 1/10 times 2/3 times u, which is 5x squared plus 4 to the 3/2 power. Now, since that's in terms of x, I'm going to evaluate that definite integral between 0 and 1. Let's see if we can clean up some of those fractions. 2 goes into 10 5 times. That's about it. All right, so I've got 5 times 3, that's 15th. I'm just going to leave that out in front. If I put a 1 in for x, I'm going to have 5 plus 4 to the 3/2 power. And then I'm going to put in 0 for x. Remember, we subtract that lower limit, so I'd have 0 plus 4 to the 3/2 power. Now 5 plus 4 is 9. The square root of 9 is 3. And then the top number says cube that, so that's 27. Here we have the square root of 4 is 2 cubed is 8. And 27 minus 8, I believe, is 19. So my answer should be 19/15. And again, try to work in fractions as opposed to decimals. Get that exact answer. All right, let's look at this problem. Again, much more complicated. If you have something in the denominator, you might want to rewrite that as a positive exponent. So let's see, if I rewrote this, could it be 0, 1, 2x plus 1 to the negative 1/2. Again, you've got a complicated expression to a power, so I'm going to let the inside part equal to u, then take the derivative, don't forget that dx, and then compare. I don't have a 2 there, so I need to get rid of it, so I'm going to divide both sides by 2. And that's legal as long as it's a constant and not a variable. So as I rewrite this, I'm going to, again, not worry about those limits because I'm going to just work in terms of u. I've got u to the negative 1/2, that's this part. Now dx equals 1/2 du. So let's integrate that, keeping that constant, adding 1 to the exponent, and then multiplying by the reciprocal of that, and that would be plus c if it's indefinite. Now I'm going to go back and change u into terms of x, so that's 2x plus 1 to the 1/2 power, but instead of plus c, I'm going to go back to my limits in terms of x, 0 to 1. So let's see, I've got 2 plus 1 to the 1/2 power minus 0 plus 1 to the 1/2 power. So the 1/2 power is the square root, so that's the square root of 3 minus the square root of 1. Final answer. If you're reading the book, they're going to go through and change those limits of integration in terms of u. That's okay. I just think that's a harder process in my opinion. I like to go ahead and integrate in terms of u, then change it to x, and then use the original limits. Just leads to probably less mistakes. Right, so again we have a square root, so we've seen that before. Anytime you have a power, you can't just use the power rule. Let u equal to what's being raised to that power. Now that's a problem because, okay, so this is u and this is du, but I've got this extra variable. I can't just add that in. A little bit different. So let's come back up here and solve for x. So let's see, if I subtract 1, u minus 1 equals to x. Let's see if that's going to help. So x, again, I'm replacing this with u minus 1, and then this is u to the 1/2 power, and this is du. That doesn't look much better, but maybe it is. What if I go ahead and distribute that? So remember, we add the exponents, so that's be u to the 3/2 minus u to the 1/2. Well, I think I can integrate that just using the power rule. So add 1 to the exponent, multiply by the reciprocal, same thing here. And if it was an indefinite integral, I'd have a plus c, but I don't. I have a definite integral, but it's in terms of x, so I need to go back and put in what is u. So I have 2/5, and u is x plus 1 to the 5/2. And I need to integrate all of that between 1 and 4. So if I put in 4 plus 1, that's 5 to the 5/2. Put in 4 here, that's 5 to the 3/2. And then I'm going to subtract by putting in 1. So 1 plus 1, that's 2. So we could go ahead and rewrite this maybe in terms of square roots. We could distribute that minus sign. Let's see, I'm going to make this 2/5 times the square root of 5 to the 5th power minus the square root of 2 to the 5th power. That's these two terms. And I'm going to come back and get those. So let's see, that's going to be minus 2/3 times the square root of 5 cubed, and minus would be plus 2/3 square root of 2 cubed. Alright, this answer is just entirely too ugly. Let's see if we can kind of go back and review about square roots. Right, so if I have the square root of 5 to the 5th power, that's the same thing as the square root of 5 to the 5th underneath. So that's really a bunch of 5s. So if you recall, you can simplify those square roots. So you can take out a 5, take out a 5. So that would be 25 square roots of 5. If we have the square root of 2 to the 5th power, we're going to do the same thing. We'd have the square root of 2 to the 5th. So I can take out a 4 and leave a 2. Then I have the square root of 5 cubed and the square root of 2 cubed. It's probably been a long time since you've done something like this, but hopefully it's coming back. Right. So let's see if we can replace those ugly things with perhaps these better looking things, or at least it looks better to me. Alright, so I've got 2/5 times square root of 5 to the 5th. So that's 25 square roots of 5. Then I've got minus, I'm going to go ahead and distribute there. That's 2/5 times 4 square root of 2. Then I've got minus 2/3 times 5 square root of 5 plus 2/3 times 2 square roots of 2. Well, I do have some like terms, but let's go ahead and kind of maybe simplify some of these fractions. So 5 goes into there 5 times, so that's 10 square roots of 5. If I multiply that, that's going to be minus 8/5 square root of 2. Multiply those two, I've got 10/3 square root of 5. Multiply those, I've got 4/3 square root of 2. Got 10 square roots of 5 minus 10/3 square roots of 5. As you recall, we can keep the radical square root of 5 and just add or subtract the coefficients. So 10 minus 10/3, that would be 20/3. Then I'm going to keep the square root of 2, and I have negative 8/5 plus 4/3. So finding a common denominator, I'd multiply by 3. So that's negative 24/15 plus 20/15. Alright, so if we add those two fractions, we would get negative 4/15, which I think looks a little bit better, but not great, but I think that's where I'm going to stop. The complicated thing about this problem, besides the ugly answer, is this little trick right here, knowing that you've got this extra x, and what do you have to do with it? Oh wow, we've got some e's. Let's just remember that the integral of e to the x dx is just e to the x plus c. So that's pretty easy. So if I rewrite this as e to the t dt minus the integral of e to the negative t dt, this one just fits our straight formula. This one we've got to do some u substitution. So if I let u equal to negative t, then du is negative dt. And I just want to solve for dt, so if I divide both sides by negative 1, let's go ahead and write this. This is e to the t dt minus, right, this would be the integral of e to the u, and then dt right here is a negative du. So I've got a negative here du. So that's going to become plus. This just integrates as e to the t plus, that's e to the u. But we've got to go back and substitute in what is u. And we don't need plus c anymore because these limits were in terms of t, so I can go between 0 and 2. So we put in our limits, e to the 2 plus e to the negative 2 minus e to the 0 plus e to the negative 0. This is e to the 2 plus 1 over e to the 2, making that a positive exponent. Now don't think this is 0. It's not. Anything raised to the power of 0 is 1. Not a limit, that's just what it equals to. And this is 1 over e to the 0, so that's 1 over 1, which is 1. So what we have, that's 2, and then we have this minus sign, so that's minus 2. And that should be your final answer. Now that looks like a scary problem. When you have a quotient that doesn't look quite so easy, I always try to look at the denominator, and let's let u equal to that denominator. Don't forget that dx. Now let's compare. Let's look at that numerator. Kind of close. What if we factored out a 3? then this right here is exactly the numerator. So I just need to divide by 3. So let's rewrite this. What have I got? On the bottom, that's just u. This top part is going to be, if I divide both sides by 3, is going to be 1/3 du. Now doesn't that look a lot easier? And you're going, well, what's that? Du over u is the natural log of the absolute value of u plus c. So if I integrate that, that's 1/3 times the natural log of the absolute value of u plus c. Let's then go back and put in what is u, and we don't need the plus c because we're going to integrate with respect to x between 1 and 2. That's 8 plus 12 minus 1. That's 19. That's 3. You can leave that like that. You could also rewrite it a whole bunch of different ways using your rules of exponents. If you factor out the 1/3, you might remember when you subtract 2 logs, that's the same as dividing. But the computer should accept any of these as appropriate correct answers. Then you're going to get to some problems that should look very familiar. It just says find the area of the region under the graph. Well, that is what the definite integral is. And so this is just another way of writing this problem, and our limits are from 0 to 1. I think that's probably the easiest problem on the homework because we just get to use the power rule. I don't need to use any u substitution. So I have x to the 4th over 4, x squared over 2, integrating between 0 and 1. Of course, that's all 0. So 1/4 plus 1/2 is 3/4. Really doesn't get any easier than that, hopefully, if you know your power rule. So then you're going to get to this average value. If you think about what average is, you add them all up and divide by how many you have. Well, the integral, remember we're adding up the area of a bunch of rectangles, an infinite amount of rectangles. And so then if we have so many rectangles and then divide by how many we had, that would be the average value of that function. Pretty easy. You notice we're just going to take the definite integral and multiply by 1 over b minus a. So let's just set this up. So that's a, that's b, so I integrate between -1 and 2. Here's my function. And then I need to multiply by 1 over b minus a, so that would be 1/3. And once again, we just get to use the straight power rule. We want to integrate that between -1 and 2. I'm going to reduce that. And all those ugly fractions come out to be a pretty easy answer. Alright, so just to kind of sum it up, this was the definite integral using a lot of substitution. They didn't give us any opportunities to use those two rules, but I have a feeling we're going to get that in the next few sections. So we really need to practice those definite integrals and use substitution.